like, I don't know, Marx and Engels. You know, they're usually mentioned in the same sentence. So they're very, you see that they look very similar, especially, you know, if you put your head like this, then Hankel looks like Toeplitz and Toeplitz looks like Hankel. But in fact, they're very different classes. So we will see in a minute. So, once again, so this is the symbol. This is a bounded function on the unit circle with Fourier coefficients an. So for Toeplitz, the key facts are the following. One, the norm of the Toeplitz operator is the same as the L infinity norm of the symbol. Toeplitz operator is always non-compact unless it's zero. So this is, by the way, very clear from this structure, because, for example, suppose A naught, the Fourier coefficient A naught is non-zero. Then on the diagonal, you have a line of constant coefficients, right? So then if you write something like TA Zn, comma Zn, this is a constant thing, right? This is a constant on the diagonal. And Zn, this is a sequence that weakly goes to zero. It's an orthonormal basis in your hard disk space. If it weakly goes to zero, compact operator must map it to a sequence that strongly goes to zero. So it's not possible for this to be constant. So it's clear that that this operator is typically non-compact. So the essential spectrum for continuous functions is very easy to describe. This is the image of the unit circle by the symbol. In general, you can imagine if there are some discontinuities or wild behavior of the symbol, then it is a much more difficult problem, and we will not go there at all. So again, for continuous symbols, the kernel, whether the kernel is present or not, whether you have a non-trivial eigenvalue or not, is very easy to describe just by looking at this winding number of this function of the symbol. Okay, now over to Hankel. So this is the Hankel operator. So the structure is different. The thing to note is that a symbol is not unique for Hankel operator, because Hankel operator depends only on coefficients, on Fourier coefficients with indices, with non-negative indices, A0, A1, A2. It doesn't know anything about the negative ones. And so if the analytic parts of the symbols are the same for two functions, then they give rise to exactly the same Hankel operator. So because of this, so there is a trivial bound that the norm of the Hankel operator is less than or equal than the L infinity norm of the symbol. But because we don't care which symbol to take from this class, we can put the infimum here. Okay, so this is a kind of a trivial bound, but the non-trivial part due to Zevni-Hari from 1957 is that in fact you have an equality here. And in fact, this infimum is attained. So you can always choose a bounded symbol such that the norm of your Hankel operator equals to the L infinity norm of the symbol. So this is the start of the modern theory of Hankel operators in 1957. So a much older theorem due to Kronecker in the 1880s is that Hankel operator is finite rank if and only if the analytic part of the symbol is a rational function. So by the way, if it's a polynomial, then this is completely trivial, because if it's a polynomial, it means that only finitely many of those coefficients are non-zero. So clearly your matrix just becomes finite rank, right? You have only finitely many non-zero elements here. And then we saw an example of rank 1 Hankel matrix corresponding to a rational function, and so it should not be surprising that this theorem holds. In some sense, a combination of Kronecker's theorem and Nihari's theorem is Hartmann's theorem, proved directly next year after Nihari's, that Hankel operator is compact if and only if you can choose the symbol to be continuous. Okay, so in some sense, you take a closure of rational functions with respect to L infinity norm, you get continuous functions. So roughly speaking, when you look at this Hankel operator, it's intuitively what happens that you see it is the faster these coefficients go to zero, the more compact this operator becomes, right? So this can be expressed in different precise ways. Vladimir Peller became famous in 1980s when he proved, when he established conditions for the inclusion of Hankel operators in Schatten class. So these were in terms of inclusion of these symbols to certain Bessev classes. So I will not go into that at all. Okay, so these are the basics, the kind of the minimal, the absolute minimal that we need to know for about Hankel interpolates operators. But our focus will be on subspaces, on eigenspaces and Schmidt subspaces. All right, so in terms of the Hardy class, remember that we define interpolates operators like this. So projection, multiplication by symbol, and Hankel operators like this, multiplication. And here we have this flip, which maps analytic functions into anti-analytic up to constants, and then again projection. But in fact, you can study Hankel interpolates operators pretty much just based on these commutation relations. So if you have a bounded operator satisfying this commutation relation with a shift, then it's interpolates, and if it satisfies this one, then it's Hankel. So that's all you need to know. Next part of Tuesday's lecture was about the structure of Hardy space. So I recalled the structure of inner functions. So bounded analytic function is inner if it's equals to 1 almost everywhere in the unit circle. And all such functions can be written down as a product of two factors. The first is a Blaschke product, finite or infinite, which has 0 somewhere in the unit disk. And the second one is a singular factor, which is responsible for some sort of some singular behavior at the boundary on the unit circle. Next, absolutely fundamental theorem, Berling's theorem, says that, as we discussed last time, that a subspace is invariant for the shift operator. Non-trivial subspace is invariant for a shift operator if and only if it can be represented in this form, inner function times the whole of H2. And by the way, this is the point where you have to have the picture of Hardy space in the unit disk in the following sense. Remember, in the beginning, I said that Hardy space, you can think of it in 3 alternative ways, either as little L2 in terms of Fourier coefficients of functions, or as Hardy space on the unit circle, or as Hardy space in the unit disk. Okay, so this is the point where the first picture becomes useless, right? So you can start by thinking of shift operator as an operator acting on the coefficients, just shifting coefficients, but you cannot have this description in these terms, in the intrinsic terms of little L2, because there is no good description of inner functions in the intrinsic terms of little L2. It's not so clear how to describe and the fact that the function is inner if you just look at its Fourier coefficients. You have to go to the unit disk to understand these effects. Okay, so then a corollary that a subspace, a non-trivial subspace, is invariant under the backward shift if and only if it is a model space. So we define these model spaces. We saw that algebraically they form a very nice lattice, right? So they're ordered by inclusion, and this corresponds to divisibility properties of inner functions. And this is the kind of this is the standard family of subspaces of Hardy space with nice structural properties. You should think of them as sort of small subspaces in the following sense, that this theta H2 is large and what is left over is small. Small in the sense that they typically have much better smoothness and structural properties than all of H2. So functions from H2 can have rather singular behavior as you approach the boundary of the unit disk, but the functions from k theta, from model spaces, you can quantify in what sense they are regular as you approach the boundary. But I will not go there. So this is just for information. Okay, a sort of a small technical point, but very important. We will use it several times. That the function 1, the function that is identically equal to 1, is an element of model space if and only if theta of 0 equals 0. And this is in many ways the simplest case. So we will often just look at this case. Then the last thing we discussed last time was isometric multipliers on k theta. So the definition is this: the multiplication by a function acts on this subspace k theta isometrically. And we discussed the theorem of Sarrazin that how to construct a rich family of such multipliers. So you write P as this ratio, A over 1 minus theta B. Theta is the same theta as in k theta. And A and B are two functions such that mod A squared plus mod B squared is 1. On the almost everywhere on the circle, right? This is on the boundary. Then this is an isometric multiplier, and we have checked it in some particular case. So this exhibits a rich space, a rich set of such multipliers. So it's a non-trivial notion. So this is where we stopped last time. Now let me continue. So one remark I want to make is that if 1 is an element of the model space, this is what I mentioned here, then this P, the isometric multiplier, can be understood as the normalized projection of the element 1 onto this space P k theta. Okay, so let's try to understand this. So suppose we just take any element of k theta and multiply it by P. Okay, so we get an arbitrary element of this P k theta space. So if I take inner product with 1, then of course, because 1 is a reproducing kernel on the whole Hardy space, what I get is P of 0, F of 0. Okay. Now, if I take the inner product of PF with P, what is it? So I write P as P times 1. Now 1, remember that now 1 is, by assumption, is in our model space. And so because P is an isometric multiplier, it acts as an isometry on k theta. And so I can remove P from both sides in this inner product. So I get F, 1, and that's just F of 0 by the same reasons as before. So P of 0 here is just a normalizing factor, so we are not worried about it. But basically, we see that the element 1 acts on all elements of this subspace pk theta in the same way as P, right? So because P is in k theta, of course, because P times 1 is P. Sorry, P is in P. Forgot to say, so P is in P k theta because P is P times 1. And so we see that P is a projection of 1 onto this subspace. So it's not terribly deep or important fact, but we will use it in the future. So I wanted to talk about it here. Okay, so let's move on. So the next thing I want to discuss is Frostman shifts. So just a second, I just rearrange my screen so I see what I need to see. Yes, okay. So there is a family, a standard family of conformal maps from the unit disk onto the unit disk. So these are called Mobius maps. So you see these are the same elements, the same functions that enter as a Blaschke in the Blaschke product. So these are sort of Blaschke factors. So there is a point of view on complex analysis that anything that you do in the unit disk should be invariant with respect to these Mobius maps. So now if we have an inner function, we can take this combination, this new function, and again it will be inner, because if theta had on the unit disk absolute values on the boundary of the absolute value 1, then because mu maps unit circle into the unit circle, we still get, so this is still an inner function. So now the question is this: how is the inner space k theta related to the inner space k, to the model space k theta alpha. Okay, so it turns out that there is a very simple answer. So let me write this answer and then I will discuss it. So so this is the answer. So this guy in front of k theta is an isometric multiplier on it. The fact that it is an isometric multiplier shouldn't surprise you, because this is an instance of Sarason's theorem for a particular choice of these functions a, b that we saw when they're constants. So let me go back one page just to remind you. Here, right? So imagine that we take for a and b just constants, right? Then instead of a, I can write square root of 1 minus b squared. So that's exactly what happens in our case, but in different notation. Okay, so I write here, here I've got 1 minus, so alpha is a constant, 1 minus alpha theta, and here this is another constant. So by Sarason's theorem, this is indeed isometric multiplier. The fact that these spaces are equal is not too difficult, and in fact in the lecture notes I sort of stated it as a sequence of exercises to check this, but now I will not go through this. So as a consequence of this fact, we can give an answer to the following question. So suppose we have some subspace which is represented as p k alpha. Now one can ask, are these parameters p, sorry, not k alpha, k theta, right? K theta. K theta, where theta is an inner function. So the question is, are these parameters p and theta unique? So of course they're not completely unique, because you can always multiply both p and theta onto some unimodular factors, and this will not change the space, right? If you multiply any function by a unimodular factor, this doesn't change the space. But in fact, you can do more. So this example tells you that you can do these apply these Mobius maps. So these are called Frostman shifts when you do this to theta, and then you just get one subspace into another subspace. So for example, coming back here, I can just take, if I had, so let me move this a little bit. So k theta alpha. If I had some isometric multiplier on this space, then I could write it here as well. Okay. So on both sides, I will have, on the left side, I will have this whole thing will be an isometric multiplier on k theta. On the right side, I have p, and so we have this non-uniqueness. So it turns out that this is the only way in which you have non-uniqueness. So the exact theorem, due to somebody called Crowfoot, who was a student of Sarason, so almost everything here in this business originates from Sarason, his pupils. So the theorem says the following, that if you have such situation, such one subspace can be represented in two ways, either as p k theta or as p tilde k theta tilde, where theta are inner functions and p is isometric on k theta, p tilde is isometric on k tilde, then in this case, you always have that theta is up to some constant theta alpha, and p tilde is up to some other constant. The first p times this factor, right? Times this factor, 1 minus alpha squared, 1 minus alpha bar theta, right? I hope I put it on the correct side. Maybe on the wrong side, maybe the other way around. But you know, you get the idea. So this is the only family of transformations that can that is possible in this case. Okay, so this is just a yeah, and in particular, the most important use of this would be to make sure that theta is equal to 0. So if you start with some k theta, you can always choose alpha equals theta of 0. Then this theta alpha of 0 is 0, right here. So if theta of 0 minus theta of z, so this vanishes at 0. And so we will have this k theta represented in some in an alternative way, right? With this, I just flip this upside down, so I write it as 1 minus alpha theta k theta alpha, and now theta alpha already vanishes at 0, and so this will be convenient. Okay. Any questions so far? So this is just a technical point about normalization. The point is that if you are dealing with a weighted with such space p times k theta, you can always ensure that theta vanishes at 0. Okay, let's move on. So the next topic is nearly invariant subspaces. So first of all, let me give you some heuristics. So suppose we have a bounded analytic function p, and we consider the operator of multiplication by p, which can be written as a Toeplitz operator with the symbol p. So the question is, how does TP interact with the backward shift? So it's an easy computation that the commutator of this is rank 1. Okay, well, indeed, let's just very quickly do it. So if you have p, if we apply this to a function f, right? So then I've got p of z, f of z minus p of 0, f of 0 over z. That is, I'm applying s star to pf. Now I can add and subtract p of 0 f of z no, maybe the other way around. So let me see. So p, let me do this, and then I will see if this is correct. So I think I need to put let me put p of z, right, f of 0, p of z, f of 0, p of z, f of 0. Then in the first term, then this term is just p times s star of f. So this is p times star f, and the second one is s star f multiplied by f of 0, and f of 0 is precisely this. This corresponds to precisely this rank 1 operator. Okay, So, it's not so important what is on the right-hand side, but the lesson is that this is rank 1. Okay, so backward shift commutes with multiplication operator up to rank 1, and so much of the underlying operator theory in all of this business is something that is related to the theory of rank 1 perturbations of various operators. Okay, so this is some heuristics to give you. Now let's move on. And so based on this calculation, we can ask the following question. So how does backward shift act on weighted on this model space to which we have applied an asymmetric multiplier? Remember that model spaces are invariant, are precisely those that are invariant for the backward shift. So what happens if we apply an asymmetric multiplier? So it turns out that they are invariant up to rank 1 subspaces. Indeed, this is precisely what this calculation tells us, that if we apply, so let's write this down precisely. So if we apply backward shift to PF, we get P times this plus S star F F1. And now this term will be, if F was originally, if F was in K theta, then this guy will be in P K theta, and this is some extra term. So in order to kill this extra term, we just need to require that F vanishes at 0. So up to restricting to the subspace of codimension 1, a star acts in an invariant way on this subspace. So this motivates the following definition due to Heat in 1988. So many of these things happened in the end of 80s of these developments. So he introduced the following definition. So if you have a subspace in H2, so closed subspace, so this is called, such subspace is called nearly invariant. Nearly invariant if it is invariant for, invariant for the backward shift up to codimension 1 in the following sense. Okay, so if you take any element of this subspace, you require that it vanishes at 0 and act on it by a star, then you get back to a star. Okay, so in other words, more concretely, for any F in your M, such that F vanishes at 0, F of Z over Z must be in M, right? So if you have a 0 at 0, you can divide by Z and you remain in this subspace. So so this is called nearly invariant. So it's a funny name. Heat originally called it, I think, something else, weakly invariant, but then Saracen very quickly had his own version of the same, his own proof of the same result, and he changed the name, nearly invariant, and it stuck. Okay, so let me make one little remark, that if M is nearly invariant, so it should be really nearly S star invariant. Let me, nearly S star invariant. nearly star invariant, then M as a subspace is not orthogonal to 1, which means that 0 is not a common 0. The origin is not a common 0 of all elements of M, right? So not all functions in M are simultaneously orthogonal to 1. Not all of them simultaneously vanish at the origin. So why is this so? Well, suppose all of them actually vanish at the origin, right? We take any element f, and by the nearly invariance, we can divide by z. Okay, we divide by z, right? We still remain in the subspace. Then we again divide by z. You know, if we still have 0, we again divide by z. If it's 0 of multiplicity 10, we can divide by z to the 10th. And so eventually we divide out the 0. And so we arrive to a function which does not have a 0, which is a contradiction to this fact. Okay. So so if nearly invariant subspaces are always non-orthogonal to 1. That's just a little technical remark which we will use in the future. Okay, so now yeah, so this is the definition, and so as we already saw that if, well, essentially this was the previous calculation, that if we have a subspace invariant for the backward shift, and if P is an isometric multiplier on this subspace, and P of 0 is non-zero, then P n is nearly a star invariant. This is precisely the calculation we've had on the previous page. And this condition, P of 0 is non-zero, means that this subspace, this whole subspace, is not invariant, is not orthogonal to 1. So this is what we call M on the previous page. It's not orthogonal to 1, because if P vanishes at 0, it multiplies everyone, and so everyone is orthogonal to 1. Okay, so Heat's theorem gives a converse to this statement. It says that if you have a nearly backward shift invariant subspace, then it can be represented in this form. So let me state it. Theorem due to Heat in 1988. Heat, I checked him out. It seems that this was his only paper. He did his PhD in Stanford, and then this was his only publication. And Saracen was in Berkeley, so they were not too far. So okay, so this is Heat's theorem. So every nearly S-star invariant subspace M is of the form M equals P n, where n is backward shift invariant and P is an isometric multiplier on n, on yes, on n. So this is let's just pause and let me emphasize the following. So this theorem gives a structural description of subspaces that are described algebraically. Okay, so algebraic description is what we had on the previous page. It's this one, right? It's just algebraic. And here we have a structural description. It's isometric multiplier times something that's invariant. because we have a structural description of those, of backward shift invariant subspaces. So we can expand this. So we have two. So we have two possibilities. We have either first possibility is that M is P k theta, where theta is an inner function. Or the second possibility is that N is the whole space. So this corresponds to N being k theta, of course. The second possibility is N being the whole space. So it may happen that M is P times the whole space. And then P has to be inner, because if you have an isometric multiply on the whole of the Hardy space, it should better be an inner function. It should be 1 on the unit circle. So this is Heat's theorem. So it is crucial in this topic. And what I will do, I will give some ideas of the proof. So I will certainly not give the whole proof, but just sort of discuss some ideas. Okay. So first let's give some heuristics. So suppose we know that M is P k theta. How do we identify these parameters P and theta? Right. So in the proof, we have to somehow to identify them. So the idea is the following: you make a Frostman shift. By Frostman shift, we can choose theta vanishing at 0, right? So if theta doesn't vanish at 0, we make this shift. Remember, this is what we discussed 10 minutes ago. And then we come up with other parameters, P and theta, such that theta of 0 equals 0. Then identity is in k theta. And so then by another remark that we discussed before, then P is a up to normalization, a projection of 1 onto our subspace M. And this is exactly what this proof does. So we start with this subspace. We know nothing about it except for this algebraic condition that S star M intersected with 1 orthogonal is in M. And then we take a projection of identity onto the subspace, and then we try to prove. So we take P normalized projection of 1 onto M, and then we try to prove that 1 over P, that the shift operator acts invariantly on 1 over Pm. That's the idea of the proof. That's at least this is how it starts, rather. So let me discuss this. Okay, so I will just give some steps of the proof. Let me maybe move to the next page, because there will be some calculation, and I want all of this calculation to be displayed. So so once again, what we know is we have that our subspace M is nearly a star invariant, and P is the normalized projection of 1 onto M. Now let's do the following calculation. It's really beautiful calculation. I love it. So we take F in our subspace M, and for it we write it in the following form. We write it as some constant times P plus F1, where F1 is orthogonal to P. Okay. So what happens? So P is an element in our M, right? So we can consider the projection of F onto P plus something else. Okay, so this is just writing down the component of F along the direction of P plus something else. Okay, now of course everything, all elements here are elements of M, because F is in M originally, P is in M, and so F1 also must be in M. By orthogonality, we have the relation this one. Okay. Now, what does it mean that F1 is orthogonal to P? It means it's orthogonal to the projection of 1 onto our subspace. So it's actually orthogonal to 1, right? So F1 is orthogonal to 1. That is, F1 vanishes at 0. And so by the nearly a star invariance, we can divide through by Z, right? So F1 of Z over Z is in M. So now let's take this F1 and repeat the same thing for F1 again. We write F1 over Z. Again, we write it as C1 times P. So the projection onto P plus whatever is left. So again, we have the norm relation. P is normalized, so I'm not writing the norm of P here. Normalized to 1. And on the left-hand side, of course, division by Z on the unit circle has norm 1. And so again, I don't need to write it down. Okay. So again, F2 is orthogonal to P, which means that F2 vanishes at the origin, so I can divide through, and so on and so on. I repeat the process. So continuing recursively, what I get that Fn over Z is Cn P plus Fn plus 1, Fn plus 1 orthogonal to P, and I have this formula. Okay, so now let's link it all together, all these equations. So we come to the nth point. So we don't continue to infinity at this point, but we just stop at the nth step and we link these equations together. And so what we get is that f of z becomes, so here we have this polynomial c naught plus c1z plus dot 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 plus cn zn p of z plus zn f n plus 1 of z. And if we link together all these norm equations for the norm, what we get is that the norm of f squared equals the sum of these coefficients plus the norm of f n plus 1. And we throw away this n plus 1. So we get an estimate. Okay, so now we can start thinking of sending n to infinity. Okay, so what we see is that if we then send n to infinity, then this sum is finite. In fact, it's bounded by f squared. And so we can consider the function this function, and this is an element of H2. Okay. Now let's see if we look at the first line here, we interpret this as simply a Taylor expansion of f at 0. So we see that we have some coefficients, and this is the this is of the next. I mean, comparing the Taylor expansion, what we find is that f of z we can simply divide through by p of z is precisely this function. All right, so we examine this as a Taylor expansion at 0, and then we, because Taylor expansions uniquely define analytic functions, so this is true as an identity on H2. And so furthermore, the norm of f over p, so this inequality simply means that the norm of f over p is less than or equal to the norm of p. Okay, so let's take stock of what we've done. What we've proved is that the operator of multiplication by 1 over p, if we consider it as an operation from M to on the whole Hardy class, is a contraction. This is not everything, right? This is not the end of the story. But this is a kind of a start of something else. So this is the first step. But the second step, we consider the set, let's call it M naught, where actually, so this is the set of all f in M, on which this operator T1 over P acts as a isometry, where you have this equality. Okay. Now, it's a priori, if you look at it, it's not even clear that this is a subspace. Right? Just take an arbitrary operator and consider a set of vectors where it acts as an identity, as an isometry. It shouldn't be a subspace. But because we've already proven that this is a contraction, then it is a subspace. It's an easy exercise to prove. If you have an operator which is a contraction, then you look at the subspace where it is isometric, then it is a subspace. So this is easy to prove. It's also not so difficult to check the following, that if you look at this subspace and M naught and you multiply it by 1 over P, okay, so if you multiply this M naught by 1 over P, then S star leaves this subspace invariant. Well, essentially, so let me explain the how it works. So what does it mean for a function f that you have this isometry here? It means precisely that here you have not inequality but equality, right? Now that means that this term fn plus 1 squared must go to 0 as n goes to infinity. And so then you can check that if you, at the initial step, you go from, if instead of f, you consider this f1, so that is the same as acting by backwards shift on this whole thing, on this factor, then this property will be retained. So still in the limit, you will have equality. So I will not go through details. So in the lecture notes, I gave this last fact as an exercise to check this invariance. This is very easy. Now, the last completely non-trivial part of it, the non-trivial part of Heat's proof, Heat proves that actually this M naught is the whole of M. So this is some clever calculation with reproducing kernels that I'm not ready to reproduce here, but he does it. He proves that this is actually the whole space, and that gives you all we need, right? So this space 1 over Pm naught will be what we called by n. It's a star invariant, and P acts isometrically on it. So this is the proof of Heat's theorem. Okay, so now my plan is to use this Heat's theorem to describe invariant, to describe eigenspaces and Schmidt subspaces of tuplets and Hankel operators. So that's the plan. So our next step is back to tuplets and Hankel operators, and we start by tuplets kernels. I forgot my numbering. So what is this? It was 11, so this is 12. Number 12. So we discussed tuplets kernels. So as already mentioned, tuplets operators are precisely the ones that satisfy these fundamental commutation relation with backward shift operator, and this is what will be mostly important for us here. Yeah, so again, as I already mentioned, describing tuplets kernels is the same as describing all tuplets eigenspaces, because if we want to describe an eigenspace of a tuplets operator, this is the same as to describe the kernel of this tuplets operator. So for Hankel, by the way, this is not the case, because identity is not a Hankel operator. Identity is a tuplets operator, but not Hankel. Okay, so now let me state a theorem due to Eric Hayashi, who was Sarason's student in the 80s, describing all such tuplets kernels. So the theorem says the following. So let T be a bounded tuplets operator with non-trivial kernel. Then there exists an inner function theta and an isometric multiplier p on k theta, such that this kernel is represented in this form. So that's the main result for tuplets operators. You know, this is not the only thing you can prove for tuplets operators, but in this mini course, I'm focusing on this aspect. Okay. So let me give a simple example. Before we come to the proof. So suppose we have a tuplets operator whose symbol is the complex conjugate of an inner function. Okay. So then what is its kernel? Right? So what does it mean, this equation? So we write P of theta bar F equals 0. So this means that theta bar f is orthogonal to H2. And this means that because theta is 1 on the unit, in absolute value on the unit circle, we flip it to the right. So it means that it's orthogonal to theta H2, and that's exactly our definition of a model space. Okay, so in this case, we see that the kernel of this operator is precisely our model space k theta. Okay, so of course k theta can be written as 1 times k theta. So here the isometric multiplier is just 1. So that's a kind of simple case, but nevertheless, it's a nice example. Okay, so now I think it's a good time to take a break as per schedule. And then after the break, after half an hour, I will give you a proof, and very easy proof of Hayashi's theorem using Heath's theorem about nearly invariant subspaces. Okay. Sasha, you are muted. You wanted to say something, but if you...
Thank you.
Any questions? Any questions, please ask.